On August 30th, 2026, one of NASA's most powerful new observatories is scheduled to leave Earth aboard a SpaceX Falcon Heavy rocket. It will not travel to Mars. It will not land on another world. Instead, it will journey nearly 1 million miles from Earth and begin mapping parts of the universe that humans cannot normally see. Its name is the Nancy Grace Roman Space Telescope. Roman will search for planets drifting through the galaxy without stars. It will map invisible dark matter, investigate the mysterious force accelerating the expansion of the universe, and test technology that could one day help astronomers photograph worlds similar to Earth. It has a mirror the same size as Hubble's, but it can capture an area of sky at least 100 times larger in a single image. James Webb allows astronomers to examine individual cosmic objects in extraordinary detail. Roman will reveal the much bigger picture. And when it opens its eyes, thousands of hidden worlds and billions of distant galaxies may finally become visible. NASA and SpaceX are currently targeting launch no earlier than 7:26 a.m. Eastern Daylight Time on August 30th, 2026, from Launch Complex 39A at Kennedy Space Center in Florida. The observatory is named after Nancy Grace Roman, NASA's first chief astronomer. She played a major role in developing space-based astronomy and is often described as the mother of the Hubble Space Telescope. Before Roman became its official name, the mission was known as the Wide Field Infrared Survey Telescope, or WFIRST. That original name reveals its main purpose. Roman is designed to conduct enormous surveys of the infrared universe. Infrared light has wavelengths longer than the visible light human eyes can detect. It can pass through some regions of cosmic dust and reveal distant objects whose light has been stretched by the expansion of the universe. Roman will explore an enormous range of targets, from small objects inside our solar system to planets across the Milky Way and galaxies near the edge of the observable universe. It will not replace Hubble or James Webb. Instead, it will work alongside them. Hubble and Webb can study carefully selected areas in remarkable detail. Roman will rapidly search much larger areas and identify interesting targets for other telescopes to examine more closely. NASA describes Roman as its next flagship astrophysics mission. The observatory is more than 42 feet long when fully deployed and carries a 2.4-meter primary mirror, the same diameter as Hubble's mirror. Roman's greatest advantage is not simply how far it can see. It is how much sky it can observe at once. Its primary science instrument is the Wide Field Instrument, or WFI. This roughly 300-megapixel camera contains 18 advanced detectors and can observe visible and near-infrared light. One Roman image will cover a patch of sky larger than the apparent size of the full moon. Hubble can produce extremely sharp images, but its field of view is relatively narrow. Roman will maintain sensitivity and infrared resolution comparable to Hubble while viewing an area at least 100 times larger. Think of Hubble as looking through a narrow but powerful telescope. Roman will look through an enormous panoramic window. NASA estimates that Roman could survey the sky up to 1,000 times faster than Hubble while maintaining similar sensitivity and infrared resolution. During its first 5 years, Roman may image more than 50 times as much sky as Hubble covered during its first 3 decades in space. A survey that might require centuries using a narrow-field telescope could potentially be completed far more quickly with Roman. That speed will allow astronomers to repeatedly observe large areas and detect objects that move, brighten, fade, or explode. Roman's Wide Field Instrument will capture images covering nearly 100 times more sky than Hubble's widest exposures, and about 200 times more than Hubble's infrared images. Most of the universe cannot be directly observed in the same way we see stars, planets, and galaxies. Everything made from ordinary atoms, including Earth, the Sun, the human body, and every visible star, accounts for only a small part of the universe's total contents. The rest appears to be dominated by dark matter and dark energy. Dark matter does not produce, reflect, or absorb enough light for ordinary telescopes to see it directly. Scientists know it exists because of its gravitational effects. Galaxies rotate as though they contain much more mass than what we can see. Clusters of galaxies bend background light more strongly than visible matter alone can explain. Something invisible appears to be adding gravity. Dark energy is even more mysterious. It is the name scientists use for whatever is causing the expansion of the universe to accelerate. Roman will not take a simple photograph of dark matter or dark energy. Instead, it will observe how these invisible components affect galaxies, light, and the expansion of space. By mapping billions of galaxies across enormous distances, Roman may reveal how invisible matter is distributed and how cosmic expansion has changed over time. For much of modern history, astronomers expected gravity to gradually slow the expansion of the universe. But observations of distant exploding stars revealed something unexpected. The expansion was not slowing down. It was accelerating. Scientists introduced the term dark energy to describe the unknown cause of this acceleration. But dark energy remains one of the biggest unanswered questions in physics. Is it a constant property of empty space? Does it change over time? Is our understanding of gravity incomplete on cosmic scales? Or is something entirely different happening? Roman will study dark energy using several independent techniques. The first involves type Ia supernovae. These exploding stars have properties that allow astronomers to estimate their distances. By comparing their distances with how quickly their galaxies appear to be moving away, researchers can reconstruct the expansion history of the universe. Roman will observe thousands of supernovae across vast distances and different periods of cosmic history. The second method involves baryon-acoustic oscillations. These are enormous patterns in the distribution of galaxies, created by sound waves that traveled through the extremely hot early universe. The patterns work like a cosmic measuring ruler. By observing how their apparent size changes at different distances, astronomers can measure how the universe has expanded. The third method is weak gravitational lensing. Matter bends the path of light traveling through space. Roman will measure tiny distortions in the shapes of millions of distant galaxies. Those distortions can reveal where dark matter is located and how cosmic structures developed under the influence of dark energy. Because these techniques work differently, scientists can compare their results. When several independent measurements point toward the same conclusion, researchers can have greater confidence that they are seeing a genuine feature of the universe rather than an error in one method. Roman will use baryon-acoustic oscillations, type Ia supernovae, and weak gravitational lensing to investigate cosmic acceleration and test whether dark energy changes over time. Imagine looking through a piece of uneven glass. Objects behind it appear stretched or distorted because the glass bends light. Mass can produce a similar effect across space. According to Einstein's theory of general relativity, massive objects curve spacetime. Light traveling through this curved region changes direction. This effect is known as gravitational lensing. A massive galaxy cluster can produce obvious arcs or repeated images of objects behind it. Weak lensing is much more subtle. A single background galaxy may be distorted by an amount too small to confidently measure on its own. But Roman will observe enormous numbers of galaxies. When astronomers combine those measurements, consistent distortion patterns can reveal the hidden distribution of mass between Earth and those galaxies. Because much of that mass is dark matter, Roman can create maps of structures that are otherwise invisible. These maps could show how dark matter forms a vast cosmic web. Galaxies and galaxy clusters appear to grow along this invisible framework. By comparing dark matter maps from different periods in cosmic history, scientists can examine how structures formed and how dark energy influenced that process. Roman's wide view is essential for this work. Astronomers do not only need sharp images of individual galaxies, they need consistent measurements across huge areas of sky. That is exactly the type of observation Roman was designed to perform. Roman will also perform one of the most ambitious planet searches ever attempted. Most confirmed exoplanets have been discovered using the transit method. A transit occurs when a planet passes in front of its star from our viewpoint, causing a small temporary decrease in the star's brightness. This method has been extremely successful, but it works best for planets with short orbits that frequently pass in front of their stars. Roman will use another technique called gravitational microlensing. Microlensing occurs when a foreground star passes almost directly in front of a more distant background star. The gravity of the foreground star acts like a natural magnifying glass, temporarily making the background star appear brighter. When a planet orbits the foreground star, the planet's gravity can create an additional, smaller change in brightness. This signal may last for only hours or days. Roman will repeatedly photograph densely packed star fields near the center of the Milky Way, looking for these brief changes. Microlensing is especially useful for detecting planets that orbit farther from their stars, including worlds comparable to Jupiter, Saturn, Uranus, and Neptune. It may also reveal small planets and worlds located in or beyond their stars' habitable zones. Most mysteriously, Roman could detect free-floating planets. These are worlds that do not orbit any star. They may have been thrown out of their original systems during violent gravitational interactions, or they may have formed differently from normal planets. A free-floating planet would travel through the darkness of the galaxy, receiving no warmth or daylight from a nearby sun. Roman's Galactic Bulge Survey is designed to detect more than 1,000 wide-orbit planets through microlensing, including objects that may be drifting freely through space. Roman's second instrument is the coronagraph instrument. This instrument is primarily a technology demonstration. Its purpose is to test advanced systems that could help future telescopes directly photograph planets around nearby stars. The challenge is extreme. A star can be millions or billions of times brighter than the planets orbiting it. Trying to see a planet beside its star is similar to trying to see a tiny firefly next to a powerful lighthouse from thousands of miles away. Roman's coronagraph uses masks, prisms, detectors, and deformable mirrors to block and control starlight. The mirrors can adjust their shape to correct tiny imperfections in incoming light. By suppressing the star's glare, the coronagraph may reveal large gas planets and dusty disks surrounding nearby stars. It is not specifically designed to photograph a second Earth, but the technologies it tests could become essential for future missions attempting exactly that. A future telescope may need to block a star's light with extraordinary precision before it can photograph an Earth-like planet and analyze its atmosphere. Roman could help prove that these techniques work reliably in space. NASA says Roman's coronagraph is designed to demonstrate planet imaging performance hundreds to roughly 1,000 times better than previous space-based capabilities. Roman is sometimes compared with Hubble because both telescopes have mirrors measuring approximately 2.4 meters across. But their roles are different. Hubble transformed astronomy by producing detailed observations of planets, nebulae, stars, and distant galaxies. James Webb uses a much larger mirror and extremely sensitive infrared instruments to examine some of the earliest galaxies and study the atmospheres of distant planets. Roman is designed for scale. It will search enormous regions, discover large populations of objects, and measure how the universe changes over time. A simple comparison is this. Roman will find the cosmic forest. Hubble and Webb can closely examine individual trees. Roman may discover an unusual galaxy, distant supernova, or hidden exoplanet. Astronomers could then use Webb, Hubble, or powerful ground-based observatories to study that object in greater detail. Together, the telescopes provide wide coverage and close inspection. Roman's enormous surveys may also identify rare objects that astronomers would never know to search for individually. After launch, Roman will travel toward the second Sun-Earth Lagrange point, known as L2. L2 is located about 1 million miles from Earth, roughly 4 times farther away than the Moon. From this region, Roman can maintain a relatively stable position with the Sun, Earth, and Moon located in approximately the same direction behind the spacecraft. This environment offers a clear view of deep space and allows Roman's solar panels to remain oriented toward the Sun. The observatory will not remain perfectly still. It will follow a large looping path, known as a quasi-halo orbit around L2. James Webb also operates near L2. Roman's primary mission is planned to last 5 years, and the observatory has been designed with the possibility of supporting an additional 5-year extended mission. Its scientific data will be publicly available without a proprietary waiting period. That means researchers around the world will be able to examine Roman observations and search for discoveries that the original observing teams may not have expected. Roman is planned to operate near L2 for a 5-year primary mission, with the spacecraft potentially carrying enough fuel for 5 additional years. Some of the greatest astronomical discoveries were not the original purpose of the telescope that found them. Roman will collect an extraordinary amount of data. Each image may contain galaxies, stars, asteroids, variable objects, supernovae, and unknown phenomena. By repeatedly observing the same areas, it can reveal changes that would remain hidden in a single photograph. Astronomers may detect stars being destroyed by black holes. They may find new classes of exploding stars. They may observe unexpected objects in the outer solar system. They may discover galaxies from previously unexplored periods of cosmic history. and they may find evidence that current theories about dark matter, dark energy, or planet formation are incomplete. Roman's greatest discovery may be something no scientist has predicted. Its power comes not only from answering specific questions, but from creating a detailed record of an enormous and constantly changing universe. The Nancy Grace Roman Space Telescope is not designed to produce only one famous image. It is designed to transform our understanding through scale. Its panoramic camera will survey the sky with Hubble-like sharpness across an area at least 100 times larger. It will map the invisible influence of dark matter. It will measure how the expansion of the universe has changed. It will search for thousands of planets, including worlds that may wander through the galaxy without stars. And its coronagraph will test technology that could help future missions photograph planets resembling Earth. Roman will not make the invisible universe visible in a literal sense. Dark matter and dark energy may remain unseen, but by observing their effects with unprecedented precision, Roman could reveal their hidden structure and behavior. For thousands of years, humans studied the universe by looking at points of light. Roman will study the spaces between them, the forces shaping them, and the enormous patterns connecting them. And somewhere inside its first panoramic images may be a planet, galaxy, or cosmic phenomenon that no human has ever seen before. This is Hidden Verse, where the mysteries hidden beyond our world are finally revealed. Subscribe and join us as NASA prepares to open a new window onto the invisible universe.